I want to start off with a special thank you to Team Idaho for hooking me up with this functional dance t-shirt. Now, I was born in Idaho, so I put together a couple extra special problems just for Team Idaho this month. And here we go with the first one. Initially, a chip is placed in the upper left corner of a 15 by 10 grid of squares. And the chip can move in these little L-shaped patterns, going 2 squares in one direction, turning in a perpendicular direction, and going 1 more square. Chess players out there will recognize this as a knight move. And we're looking for the minimum number of these L-shaped moves needed to get the chip from the upper left corner here down to the bottom right corner over there. Now, this is a pretty unusual kind of problem. I don't have any special formulas. I don't see problems that look just like this all the time. That's what makes it a little scary. That's also what makes it a little awesome. Now, this problem is an optimization problem, and what that means is we're looking for the minimum of something or the maximum of something. In this case, we're looking for a minimum. Now, that means we have a two-step problem. All right, first of all, we have to figure out what that minimum number is. We have to find out what this lowest number is and show that we can actually do that. We can get there in that number of moves. And then second, we have to show that nothing lower is possible. That's how we know for sure we have the lowest one. Now, I'm not going to worry about this minimum thing when I start. First thing I'm going to do is I'm just going to play around. I'm going to try to get from here to there, and however many moves it takes, I just want to play around and get a sense of the problem. And there's 1 move, 2, 3, 4, 5. Now I'm not following any special strategy here. I'm just trying to get from here to there. Again, I'm just playing around. Not trying to do anything smart. 6, which is good because I'm not actually succeeding in doing anything smart. Let's see, 6, 7, 8, 9, 10. All right, now I'm going to stop and I'm going to actually try to do something smart because I'm kind of going around in circles here. I want to get to this X. I'm going to think backwards a little bit. How can I get to that X? Well, I can aim for this spot or this spot. These are the only 2 spots that can get to the X. I'm here in 10 moves, and now I see how to get to this spot. I go 11, 12, 13. So I can get there for sure in 13 moves. I know I can get from here to there in 13 moves, but it sure looks like we've got to be able to do better. Right? I mean, we went back and forth all over the place. There must be a more direct route. There must have been something clever we could have done here at the end. So I know that the answer, well, it's 13 or lower. It's probably lower than 13 because we're going to beat this. So now I'm going to try to be more methodical. All right, what I'm going to do is I'm going to try to get from here to this side of the board as fast as I possibly can. I'm going to go 1, 2, 3, 4, 5, 6, 7. So I can get from this side of the board to that side of the board in 7 moves. I can't get there any faster. And the only way I can get over there in 7 moves is to go 2 steps that way every single time. But that will only take me this far down the board. I can't get all the way down to the X. So if I get from the left side to the right side as fast as I can, I'll never get low enough to hit the X. So I know that my correct answer is greater than 7. I can't get there in 7 moves. Now, sitting here and looking backwards like we did before, knowing that we have to hit this cell or this cell to get to the X, I see immediately now, I also see, well, I can't get there in 7, I can get there in 9. You can go here and then here, and we're there in 9. So I know for sure 9 will work. And I know the answer is greater than 7. The question is, can we get there in 8? All right, let's try that. Let's try to get there in 8 moves. Here we go. 1, 2, 3, 4, 5, 6. 7. Can't get from here to there. All right, let's try again. Let's try again. Yeah, I'm gonna try something completely different here. Maybe they're trying to trick us with this little suggested move right there. Let's go like this. 1, 2, 3, 4, 5. 6, 7. I can't get from here to there. And well, one way I can see I can't possibly get from here to there is I'm on a light square here, and the X is on a light square, and well, every time I move from a light square, I can only go to dark squares. So I can't get from a light square straight to a light square. If I look back at my whole path, it's light, dark, light, dark, light, dark. And the chess players, of course, know this intuitively. I'm always going to be going from light to dark to light to dark as I'm moving around with these little knight moves. So my first move was dark to light, so the second move goes to dark, third is to light, fourth is to dark, fifth is to light, sixth is to dark, seventh is to light. The 7th square the 7th square is always, here it's light, here the 7th square is light. The 7th square is always going to be light. So the 8th square is always going to be dark. So we can never be at the x on our 8th move. So 8 is impossible. So we come back here. Now that we've proved it's greater than 7, 8 is impossible, 9 is right here on the board, 9 is possible. We've got our answer. We solved our optimization problems. We knocked off both parts. Now let's try this again with another problem. Try another optimization problem here. We have to remember we got a two-part problem here. And this is the problem. A, B, C, D, and E in the decimal representations of 0.ABC, 0.DE represent the digits 1, 2, 3, 4, and 5 in some order. And we want the least possible difference between these two numbers. Point ABC, point DE. So we want these two numbers to be as close as possible. So I'm going to focus on A and D first. These two, we want these two digits, A and D, to be only one apart. Because if we choose them two apart, we can make those two numbers closer by choosing them one apart. Now, if we put a 5 in at A and a 3 in at D, we know that putting a 4 in at D is better. That'll be closer to whatever number this comes out to be. So let's go ahead and start off. Again, we'll just play around. Not sure we're going to get the right answer, but we know at least the 10th digits have to only be one apart. So try 5 and 4 and see what happens. Now let's think about the hundredths places. Well, we want the hundredths place and the higher number to be as low as possible. So I'm trying to push these numbers together. I want the hundredths digit in this number to be as high as possible. Because again, I'm trying to get this one up to as close as possible as this one. So the only digits I have left are 1, 2, and 3. The lowest one is 1. The highest one is 3. And that leaves a 2. Now, where do I want to put the 2? Again, I want these numbers to be as close as possible. So I'm going to put the 2 on this number. It's going to move it up a little bit closer to the top number rather than putting it here, which would make the higher number even greater. So these two, their difference is 0.078. But maybe we can do better. All right, let's think about this for a second. We know that we want these two digits to be only one apart. And while we were working on this, we saw that we wanted these two digits, we wanted the hundredths digit of the lesser number to be as high as possible because we're trying to push it up towards the greater number. And we want the hundredths digit of the greater number to be as low as possible. So we want to push that back down. What do we want to do there? Well, let's try. We want these two to be one apart. Well, if we make this as low as possible, we could put this as a 1 and this is a 5. And then we want these two to be just one apart. So let's try with a 4 and a 3 there. All right? And then we have this 2 left over, which we can throw out here again. We know that we want to put that in a thousandths place of the lower number. And what difference do we get here? Well, the difference we get here, well, this is a lot better. We have 0.058. All right, and we beat this by a lot just by thinking about the hundredths digit after we already figured out what we're doing on the tenths digit. So now let's think about what we're doing out here in a thousandths digit. We know that we want these two to be one apart. We want this hundredths, the higher number's hundredths digit, to be as low as possible. We want this one to be as high as possible. What about this digit? We want this number to be pretty high as well. All right, so what digit higher than 2? Well, maybe we get a 3 there. Maybe we get a 4 there. That would be fantastic. So we know we want the 2/10 digits to be one apart. We want this to be as low as possible. I'm going to go ahead and peg that at 1. We want this one to be as high as possible. I'm going to peg that at 5. Can we get a 4 in over here? Well, sure we can. Put a 3 and a 2. We want these two to be one apart. And this distance, the distance between these two, is now 0.056. And we've reasoned our way through each digit, and we're pretty confident now that this is the best we can do, because we did the best we could at each point. But we can also double check, because there's really only one possibility left for the tenths digits. We know that they want to be one apart. We can go ahead and look at what will happen if we put 2 and 1 there. If we put 2 and 1 there, well, the best we can do, the lowest this can be now is 3, highest this can be is 5, and we drop a 4 in there, and this is a loser. This is 0.076, which is not nearly as good as this. So once again, we've tackled our optimization problem. We showed that this value that we found as our minimum value is possible, and we've shown that no other no other value is lower. So just remember, optimization, two-part problem. First, show that nothing better is possible, and second, show that your actual answer is possible.